everybody for joining the PWI Birmingham Sections meeting this August. So we've got Alex Bourne from Getzner, and he's going to be doing a talk focused on the latest advances in vibration mitigations, and that's for slab track systems in both the high speed and conventional rail. So a little bit about Getzner, no doubt Alex will talk a little bit about it, but they're the global specialist in vibration isolation for the railway and construction sectors. While Alex is going through his presentation, if anybody has any questions or anything, obviously drop them in the chat. There's going to be a Q&A at the end, which I will run, but I'll pass you over to Alex now. But yeah, probably don't ask or put your hand up throughout the presentation. Just try and save them for the end bit, just so the flow of the presentation goes good. Okay, Alex, over to you.
Perfect. All right, so as Kate mentioned, this will be a presentation on slab track isolation, and mainly focusing on high speed and light rail. So just that kind of an intro. I think we can all agree, like public transportation and trams, they're great. They're great for the community and cities. They take cars off the road. They're very efficient, very easy to get around. Don't have to worry about traffic, things of that nature. They're also very sustainable. You can move high capacity of people fairly easily and frequently. That also comes with low running costs, and it helps revitalize urban areas. However, with trams, you do have quite a bit of problems that might come with them, especially when you're putting them in dense urban areas. So you'll, of course, have tram-induced vibrations, which will lead to disturbance to residents while they're trying to sleep or also do other daily activities. This could also lead to also having issues with sensitive equipment, such as microscopes and other types of lab equipment. And then for some extreme cases, you could have some types of micro cracks in plaster or other types of damage to nearby buildings, especially if they're historical buildings that have been there for a while. And that's kind of where our specialty comes in. So Getzner is a worldwide expert and specialist in vibration isolation, whether that's isolating the trains or trams at the source, so isolating them. We also do full building isolation, where we would wrap our material around the building foundation and prevent the vibrations from going into the building itself. And then we have a lot of other applications for architectural acoustics, such as floating floors, and then mechanical isolation, and the list really goes on for everything we do. So our core specialty with that is manufacturing, but also engineering polyurethane. So we have our two main types are Silamer and Silodyne, and the beautiful colors you see there are all different densities of that material. So that's really where the engineering comes in, analyzing the loads, axle weights, things of that nature to control rail deflection, but also provide optimal vibration isolation depending on a wide array of variables. So for railway, we provide all kinds of solutions for railway superstructures, such as under tie pads, ballast mats, mass spring systems, rail pads, and even booted sleepers. But for the most part, this presentation is going to focus on our mass spring systems. And with these, we have three main types or strategies, I would say, to sort of implement a mass spring system. We have strip bearings, which are strips of our material that are going to be used to support the slab track. We have full surface, which is a full surface approach using mats, and then finally point bearings, which are blocks or discrete pads utilized to support that slab track. So just to cover a mass spring system in general, or a quick intro, it's also known as a floating slab track. And essentially what we're doing here is isolating the track and separating that track from its surroundings. This is going to be the highest performing isolation solution for a railway. And mainly because of that slab track and having that additional mass from the concrete. And with that, we're going to mitigate the vibrations from the train pass-bys and structure-borne noise from being transmitted to the surrounding buildings, environments, or other sensitive areas that might be nearby. And as you can also see, we have varying performance for those as well. So for mass spring systems, they do become, it is important to account for them in the design phase because they can have a lot of impacts on the track design itself. So depending on the slab track design, it could influence the structural design of the track. You're also going to have rail deflection and track stiffness changes, mainly due to the introduction of that elastic layer of material. You'll also have a track height change, which of course you're introducing another thickness or layer into the track buildup that could cause that height to change. And then another big important factor is you got to have some type of budget within the project for these solutions, and that's best to consider that as early on as possible so that they're not running into change orders or other issues down the line. And then finally, retrofit solutions are very, very difficult, if not impossible to do. So that's another thing. And then finally, when that route is defined or when the preliminary route that they want to implement for the new rail line or light rail, a noise and vibration study will be carried out to sort of predict those levels. And based on the surrounding buildings and where that track or the line will be going, vibration mitigation measures and performance will be notated and sort of given. So that's kind of an intro to mass spring systems themselves. So now I'm going to sort of focus on individual solutions and also show references for those solutions. So I'm going to sort of work my way from, full surface, which is the least performing, all the way to point bearings, which is the highest performing solution. So for full surface bearings, we're looking at a natural frequency of 15 to 25 hertz. And for the natural frequency, for those who don't know, the lower the natural frequency, the better. Whatever your natural frequency is, any vibration that are higher or have frequencies that are higher than that will have a reduction. So that's kind of why the lower the natural frequency, the more vibrations you're going to reduce. It's also an easy and cost-effective installation. This is mainly coming from point 4 that you see there. The bearings serve as loss perform work. So you can lay down their full surface solution and then pour your slab track directly on top of it without having to worry about precast elements or any other types of additional formwork there. And finally, we also have long-term performance, which is proven, and I'll get to that later in this presentation. So one reference for this is the Dubai tram, which was the first tram in this region. It was built in 2014. It was a little over 1.2 kilometers of track isolation. And this was a full surface solution using our Silamer material. And it had a reduction or insertion loss of 20 dB at 63 hertz. And this is showing you the installation process of the full surface for that project. You can kind of see you have your basis or surrounding concrete, and then you would lay down our material, which you can see in blue. Then you would pour your first slab, and then finally the top slab track, and then place in your rail fasteners and rail system there. So you can see here some of the structural slab pre-poured, getting ready to install our material. And then you can see our blue silomer being installed there. So essentially you're laying down the mats, making sure the seams are flush, and then you would tape the seams with our material. Here's a few more pictures showing using adhesive to adhere those side mats here. And then you can also see them holding back the side mats here as well prior to the pour. And just a couple more pictures showing this whole process. You would lay down your wire mesh on top of our material. Once again, no special tools are needed. It's a very straightforward installation process. And just a couple other reference projects as well, showing different configurations and installations. So that covers full surface. Next up are strip bearing mass spring systems. So with these, they're kind of middle of the range, natural frequency wise, you're 8 to 15 hertz. You also have the possible of quick and easy installation. So if you're doing actual strips with no filler material, as we call it, you're going to need to use precast elements or get creative with formwork. However, we have filler material, which is essentially soft polyurethane that would fill the voids in between the strips. So that way you're still getting higher performance in a full surface solution, but you still kind of have a full surface that you can pour that concrete directly on. And that goes to the next point, which you typically have to use precast concrete slabs if you're not using that filler material. And of course, you have the long-term performance of our Silomer or Silodyne here. So this is kind of covering the install steps. You'll see, once again, you place our material down. However, here you're using a precast slab if you're not using our filler material. And then once that precast slab is placed, you can then pour in situ concrete on top of it. It's mainly just with the voids, you can't really pour concrete or else you would short circuit the solution. So here's just a few more install pictures showing the whole process. What they did here is they actually used some formwork, as you can see, and got creative with how they were going to pour concrete in the field, which this is another solution here. And then this shows you kind of both of those solutions that I was just discussing 2 slides ago. So on the left is utilizing a prefabricated slab where the strips are laid down and then the slab is dropped on top of those strips. And then here on the right is where they cast it on site. And that black material is the higher density Silodyne. And then the yellow is our Silomer SR11, which is our softest material. And it's just literally there to act as formwork. So it'll still distribute the majority of the load onto the denser strips. However, it still does not perform as well if you did precasted elements such as this. And then one reference we have for this is actually in New York. This was a partnership with the New York City subway and the JFK airport. They were building a air tram, which connected the airport to the nearest subway center and station. For this, it was over 500 square meters of Silodyne that was used, and this also used precast concrete elements to effectively isolate this system. And you can see here some of the pictures with the precast elements on our Silodyne bearings, and also the construction process or progress there as well. And then finally, we have our point bearing mass spring systems, or discrete bearing, as you also might hear them referred to. For this, you're looking at the lowest natural frequency possible of 5 to 12 hertz. The other nice thing is usually with these, the bearings are interchangeable, meaning that the majority of them are all designed the same. So they'll have their own spacing and you don't have to worry about placing them in certain places. You'll also have, once again, long-term performance. And then there are different installation procedures possible here as well, such as pouring the concrete on site or using prefabricated slabs. Once again, here's the install, and as you'll notice, it's very similar to our strip installation. The main difference is you're going to have to coordinate where the actual bearings go rather than being placed continuously across that structural slab support. So we have another in-depth reference here to show kind of the install process. This was a mass spring system that was done in Spain. It had very high requirements, and this was mainly due to historical buildings. So this kind of goes back to what I mentioned at the beginning of the presentation. With historical buildings, it's not just the disturbance from the noise and vibrations and disturbing residents. It could also lead to possible damage of historical buildings. So that was a big concern here, and one of the main reasons for such a high performing solution. The total length of this track was about 1.5 kilometers, and we achieved a natural frequency under 7 hertz. And for this, we used Silodyne ND bearings that were 310 millimeters by 310 millimeters. So you can kind of see the install process here. Typically what's done is they'll mark and create kind of pedestals for the pads to be placed on. And then once that's done, and that's mainly there to have a nice level surface for the pads to sit on. And then once that's done, they'll lay the pads in, not necessary to do, but it's recommended to glue them down just to prevent any type of movement in the field. And that's done basically the whole length of the track that you're isolating. You'll also see the placement of the precast concrete slab. And here's a few other pictures kind of showing this process and the installation. You can see some of the sidewall material there getting ready for the pour. Just another shot of our pads being installed and floating that precast slab. And then finally getting to the pouring of the actual slab track itself that was going to be used. So these next two references I'm going to show here are going to be long-term performance references. It's something that Getster really prides ourselves on, mainly because of the long life of our polyurethane materials, but also we've been doing these types of applications for over 50 years now. So we have a lot of experience and a lot of references throughout the years. So this was for a tramway project that we did in France. What you'll see, just some basis of the line itself. It was a mass spring system using our Silomer. There was various points and stretches that were concerns due to residential locations. And basically we went back out in May of 2019, or a third-party consultant did, and performed measurements to see how the solution was performing after 15 years in service. This is just kind of giving you a map and showing you the location of where the measurements were taken along that line. And then also some pictures here as well. So the mass spring system would be the track itself, and then that orange line that you see there is that side joint, or where that vertical material would have been installed. And then what they're doing here is measuring the vibrations on the track itself and then the vibrations on the sidewalk. And that should be able to give you a good delta of this is what the vibrations are like without the isolation and then with the isolation. So essentially, the measurements were taken, and the results showed that we had insertion loss or a reduction of 23 dB, which was outperforming the initial recommendation for the project of 20 dB at 63 hertz. And so that means we were still meeting the project specifications even after 15 years of operation. So that was pretty great to see, and also showing that our Silomer solution worked for also both train types as well, as they had introduced a new train type after about 10 years of operation. And then another project that is used a lot for these long-term references by Getzner is the Vienna Opera House. So essentially, this was a third extension phase that they were going through. They were extending 300 meters, and there was various other renovations that were being done here as well. So a little bit of background for the Vienna Opera House. Its grand opening was in 1870, over 150 years ago. It's some call it the concert hall with the best acoustics worldwide for classical or orchestral music. And it's kind of the benchmark for a lot of concert halls because of that ideal reverberation time. So it's a very, big and proud opera house that's an historical. So essentially what they were doing here was, for this extension, they were going to be implementing underground rail line that would be running basically directly next to and underneath the opera house. And essentially what was being demanded was that there would be no noticeable change when you're in the opera house during underground operation. So, of course, these types of projects, as I mentioned, require analysis by an acoustical consultant. So, various types of vibration measurements and also analysis was done to sort of figure out what solution needed to be implemented, but also what performance needed to be achieved with that solution. So the expert opinion or the recommendation from the acoustical consultant was a 5.5 hertz solution, and having a 30 dB reduction at that 63 hertz. And this part of the mass spring system was going to be and 100 meters long, give or take. So with this, you can see the installation of our Silodyne NE bearings here. The construction company was involved, and first measurements and publications of this was done in 2003. And these were carried out by an acoustical consultant in the Vienna area. And you can also see our calculations shown here, showing our natural frequency and our lobe curve. So this is something that we typically show and provide for these types of projects. So it'll be acoustical performance, but then we'll also show rail deflection and additional deflections as well for the track, and kind of model what it will look like when you have a train pass by based on the given inputs for that train. This is just showing you a little bit more of the design that was done with our Silodyne NE and the installation process. So with this, they use precast elements. There's actually 48 done. And then with those precast elements, we provided 2 bearings, so one on each side, kind of in the middle of that slab track or the precast track, to isolate it. So this is just kind of giving you a big overview / timeline of how the project started and underwent. So you had the planning in 1998, which led to construction around 2000, and then startup was in 2002. They took measurements after the first year in 2003. And then finally, another round of measurements was taken in 2019. So after 17 years of operation. So for those measurements in 2019, these were done July 29th to 31st. Here's some pictures just showing you the mics that they had set up inside the opera house itself. And then also they took measurements inside the tunnel as well. So you can see some accelerometers placed on the actual slabs itself. And this kind of a picture showing that train running there. So comparing the natural frequency measurements that were done in 2003 and 2019, you'll see that there's a 5.4 hertz measurement in 2003 with a 5.3 in 2019, which showed that there was no change in performance after 17 years of operation. They also did airborne noise measurements here, where you can see the red line is basically ambient levels or levels with, you know, normal activities or nothing happening. And then the green is the measured levels when you have train pass-bys. So as long as those levels are at or below the red line or the ambient, then that means you wouldn't be able to tell a difference between operation and not operation, which means there was no disturbance from the operation, and we were able to achieve the goal that was set out by the opera house operators. And finally, just another good shot showing that slab track installation and our Silodyne pads installed. So we've done over 500 mass spring systems worldwide, covering a wide variety of continents and countries. This is kind of just a map giving you an idea of, you know, our expertise and coverage with these types of projects, and also the importance of these projects. So it's being done everywhere just because of the need of either disturbing residential buildings or also preserving historical buildings or even opera houses like I just showed you. So with this, we do have a few local examples as well that Andy helped put together for me. So I'll kind of show you a little bit more on all of these. We have the Manchester Metrolink, this was a mass spring system that was done here as well. We have the West Midlands Metro in Birmingham, which was a full surface mass spring system that was done mainly near the square to prevent any type of disturbances from tram pass-bys there. And then a little bit more detail on this project where you can see our full surface 25 millimeter Silomer solution that was utilized to isolate the track, and kind of giving you a better detail of what that installation process would look like. And then, of course, we have London Underground, which is one that we've done quite a bit of work on, whether it's mass spring systems or other type of solutions to provide vibration isolation as needed. So this was the East London line that was done, and the Crossrail Elizabeth line. So you can see our solutions. For this, we used two types of solutions depending on location. We had booted sleepers, which you can see here in the blocks. And then we also had mass spring systems that were also installed in more sensitive areas. But these booted sleepers contain our Silodyne material and is another way to isolate the rail line. And then one other just to show is one where we used our ballast mat to actually provide some type of vibration mitigation here. And this was for Tram Dublin that was done. So just kind of showing that process, and the ballast is kind of infilled on top of that. And then finally, we have also a lot of references from operators. So I know that's another thing once you get to the design phase and trying to go through and analyze providers for these solutions. We have Dutchibon here. We also have Obebe, along with various other operators from around the world. And these are all reference letters and reference packets that we can provide as needed. But really, the list goes on, just kind of showing that they've used our material and they're happy with it and certify that it works for all of their needs. So a solution, with our material and everything is great, but it's only half of the equation. You're really not getting everything. So with us, not only are we providing the material, but we're also providing technical support, and that's in the pre and design phase. I kind of showed you an excerpt from one of our calculations where we're predicting the natural frequency, but also the insertion loss. We'll also give you deflection predictions for the tracks itself. We're also good with transition zones. So for some of these areas,
that's just what I've got my hand up for. So that's just what I've got my hand up for. So it's this agreement on the transfer from SOSA post week 40 during the sort of post EIS snagging defect rectification period over to the RAM.
So with we also have the transition zones, which is important for where you have areas with high rail deflection, and then you're going to an area with no type of isolation. Sometimes that step off is too great, so we'll work on a way to implement thinner material or denser material to create a more gradual step down to allow for a smoother transition for those areas. And then we also have a very competent and experienced team, as we have in-house application engineering at our headquarters, with about 12 engineers there as well that can provide assistance. Not only that, we have very stringent quality assurance and quality control procedures, where we're testing throughout the whole production process, but we've also done a lot of tests for the pads and also systems themselves. And we can also agree on specific project requirements for testing and quality certificates as needed for the supply. And then finally, we also have commercial support, where we're working on material dimensions to optimize installation logistics, delivery on site as well. We can coordinate that. We also have the ability to provide install supervision and inspections as needed to sort of guide the install team throughout the installation process. And then various other support that we can provide during the whole project, and its various phases that will be there. And this is kind of coming on another big thing that recently happened with the UK government looking or investing 15 billion in light rail, which is something I think really great and something that will be big for the future of the UK. So that basically covers a presentation on mass spring systems, and gives you a good idea and introduction to them, along with several references and also long-term performance references as well. So do we have any questions or comments from anybody?
Yeah, I'll jump in first. Thank you for that insightful presentation, Alex. I think it's given us a lot to think about, and I'm sure everyone has got plenty of questions. So I'm going to open the floor to questions. So if anybody has one, please pop your hand up, because it's always nice to see a face. But if not, drop it in the chat. Just to kickstart things off, I'll start with a question and then we'll take it to the floor. So one of the things we're thinking about is given the UK's dense urban rail corridors and aging infrastructure, why isn't vibration isolation considered more proactively in project planning? Is it is it mainly due to cost perception or lack of awareness of long-term benefits, or do you think it's to do with gaps in design standards?
I mean, I think there's a big, there's multiple factors that go into that. So, I mean, design standards are one. There's really no specific standards for residential buildings, so it's more coming on the recommendation of the experts or the acoustical consultants. And I think another big thing is, especially that we're seeing recently, is kind of the government's play in it as well, with kind of cost cutting and trying to find ways to still build everything as they said they were, but trying to cut costs or cut areas where it's becoming not as prominent. And with that, I think that's why it's very important to show these types of solutions, and especially since these are happening all around the world. So it's not just one localized area where we're seeing these types of solutions being implemented, but really something that's being implemented around the world as a whole.
Okay, thank you. We'll take it to the chat. So we've got one here from John Gentle. He's asking, does anyone know the anti-vibration solution adopted for the Taiwan high-speed rail project when the alignment went close by the chip factories in Hsinchu that cut the wafers and near zero vibration was specified so not to interfere with the wafer manufacture process? So that's quite a big question.
I'm not familiar with what was implemented there, but that's something that we could find out from our local subsidiary, and because I'm sure we were involved at some point with that project to see what was implemented.
John, I see you've put your camera on. Did you want to jump in there as it was your question?
Yeah, sure. I think you hit the nail on the head a little bit earlier. Well, you mentioned that perhaps we were certainly in Taiwan, we had a bit of a gap. And I think they only, after they'd started the construction, they only realized that it could be a massive problem. It nearly scuppered the whole project because these chip factories, basically they're essential for the whole economy of Taiwan. And the slightest vibration when you're making the wafers can throw the whole process because you're working in nano measurements. So I think that's the gap there, is the designers really need to address this at the design stage, and then you've got a chance of being in the right solution. I can't remember what the solution was, but it took a lot of thinking about, and it was a mega cost associated with it. But anyway, just a little bit of an aside there. So anyway, thanks for the presentation.
Yeah, thank you. And that was definitely good insight there. And once again, the importance of the earlier on in design this happens, the less impacting cost as well.
Yeah, definitely. Okay, got another question from Stuart Corrie, or it could be Corrie Stewart. Sorry, not too sure which way around it is, but they said, if discrete bearings are the best performing, why would you use the other solutions you were showing?
Good question. So discrete bearings are the best performing, but based on those measurements taken by the acoustical consultants and also the surroundings that you have, the discrete bearings might be an over-engineered solution. So cost of material, there won't be a big difference. However, the actual installation and construction cost, along with the design of it, becomes a lot more complex and complicated as you add in those types of discrete bearings or strip bearings. So really it comes down to what's needed and what's ideal for those types of projects.
Stuart, do you want to add anything to that? I see you put your camera up, or has that answered your question?
Thank you. Yeah, that answered it.
Yeah, and that's why you saw for like the Opera House, the Vienna Opera House, very, sensitive, high application where you're going to need that type of high performing solution.
Excellent. Okay, we've got a few people put their hands up. So we'll go to the first one. And forgive me if I say it wrong.
That's fine.
Yeah.
That's all right.
Okay, dive in.
Yeah, hi. Thank you for the presentation, Alex. Just wondering about the actual design life of the mass spring system, or the material, and the inspection, maintenance of it? If it wears off, there's a lot of going on, isn't it? Taking the slabs out depends on the construction procedure. If it's in situ, God knows. So how's that being done?
We have multiple references. One especially not for mass spring system, but using our same silodyne material for ballast mats that's been installed for over 30 years, showing that it's still meeting project specifications. And we also have done age acceleration testing by the University of Munich, and they certified 100-year service life for our material. So in terms of our material and longevity, I don't see an issue with it. You would probably be looking into bigger issues with the concrete itself over 50, 60 years rather than degradation of our material. And another great thing about it as well is that it has very little, reactivities to other types of elements that it's going to be exposed to in those types of conditions. So anything with water is not an issue, along with oil or anything else like that it might be contaminated or exposed to.
Cool. Thank you very much.
Yeah, no problem. Thank you.
Okay, over to, I think Mark's next. If his question, if you want to jump in.
Hello there. Hi, Alex. Thanks again for your presentation. It was really interesting. I noticed on one of the cross sections where we were talking about the continuous support system. There was a drain in the middle of the forefoot underneath the structure. How does water get in there? Is the material permeable, or I'm just wondering how.
So it's somewhat permeable, but also with these types of projects, they're going to have a drainage system that they implement. So it's not just for track drainage as well. You're also going to have a lot of drainage if there's platforms or other areas. But essentially what they'll do there is implement like a drainage box that would kind of be casted into the concrete here. It's not really shown in detail. And then that would allow for runoff down the track into that drainage box. And then they would have a piping network that would go through and connect to here. And with that, we just have to make sure that we're wrapping the piping when it sort of transitions from the isolated portion to the unisolated, but that's also details that we can work through with the design team and make sure everything's captured as needed.
Okay, because really, it was making me think about if it's semi-permeable, how does it react with sort of freeze thaw with water?
So our Silomer material is a mixed cell or open cell. Our Silodyne's fully closed cell. So once we get to like the strip bearings and the discrete bearings, it's gonna be less permeable or closed cell. However, there's really no issue with the freeze thaw cycle. We have lots of project references in the mountains in Switzerland, but also some in Russia. And we actually did kind of an experiment or presentation on that itself, and taking our material, putting it, I think it was like -10 degrees C in a freezer for 24 hours, taking it out and then bending it, testing it, and comparing the results after. So really there's no issues with it, and with water in general as well.
Okay, thank you. Thanks for explaining that, Alex. Thank you.
Yeah, no problem.
Really good. Thanks.
Thank you, Mark. Next question over to Kat. He's been waiting patiently. If you're all right.
Hi, Alex.
Hey.
No, it's I'm kind of following up from the question about the life of the material, because I was more interested to know what's the comparison versus concrete, because obviously concrete can have 60, 100 years, but you already answered that. But I think the comment from me, it's when you consider floating slab track, you also need to remember that the floating slab track introduces more horizontal vibration, and that's the reasons why we don't implement it also everywhere. So I think as a designers, when we consider systems, we need to consider all the requirements, not only vibration. And obviously, from my experience, floating slab track is generally more expensive, and the cost comes to it as well. So that's just comment really more than a question, probably.
No, yeah, it's definitely once again more on the expensive side, but it's also there's really no other option if that type of acoustical performance is needed. And that's why a lot too, you'll see on that one example we used in Dublin, we'll also use our under ballast mat for vibration mitigation if needed. But just sometimes that doesn't cut the requirements set by the consultants.
No, 100%, and that's, I don't dispute that.
Yeah.
Floating slab, it's the only slab that really can, deal with vibration, as you're talking about, opera houses and, London Underground and congested cities. But obviously, the vibration requirements, they're not always as strict in every location. That's why we consider other slab track solutions as well. Okay, thanks.
Yeah, thank you.
Thank you, Kat. Does anybody else have any more questions? Or you want to write something in the chat? One of the things I noticed, Alex, you mentioned previous projects. I noticed you mentioned the Channel Tunnel. Did you have any more information regarding your involvement in that? Or
so I wasn't involved directly on it, but we could definitely provide some additional info on that because I'm sure we can dig it up in our applied application engineering department for sure.
Yeah, okay, because I'd be very interested in reading a little bit more on that bit if you have it to hand.
Yeah,
okay.
For sure.
Excellent. Okay, well, I think everybody really enjoyed that, and we can tell by the amount of different questions that we had. Everyone was very engaged. So once again, from the PWI, I just want to thank you for your time, Alex, presented to us. For everyone else, just a brief for the next meeting. So the next PWI meeting will be held on the 11th of September, but this one will be entirely focusing on the proposed PWI name change. So please do come along, listen to the reasons why the change is happening, and also use it as an opportunity to ask any questions you have. So Joan here will be presenting that, and she'll happily answer any of the questions that you have on it. Other than that, if no one's got any more questions, I think everyone's just thanking you. I will close the meeting. So thanks
Perfect.
again.
Yeah, thank you all. Hope you have a great rest of your day.
Thank you.
Thank you. All right.
All
Bye,
right.
everyone.
Thanks,
Good to see
Alex.
y'all.
Alex, cheers.
Thank you.